Welcome everyone to our second tutorial in the Cath Lab lecture series. My name is John Boland. We have a little bit of a dilemma this week and the next couple of weeks because there are 6 lectures per week and you are most unlikely to have read more than 1 or 2. This week we're covering 3 topics. You have 2 lectures of radiation and radiation safety, 2 lectures on transducers, 1 on pressure waves, and the 6th lecture on cardiac output I'll deal with in next week's tutorial because there are more cardiac output lectures to consider in the following week. We'll lump them together in one hit. So we'll start by looking at radiation. The first primary rule in the cath lab, as anywhere else that uses radiation, is safety first. You must always be aware that whenever you walk in the cath lab, there may be radiation in action. You must be protected. Always be on the lookout for yourself, the patient, and your colleagues in terms of radiation exposure. The first lecture in radiation was delivered by our first guest lecturer. You'll have a couple of more before the end of term. Cameron Jeffries, a radiation physicist. And he showed you this slide. And I'm sure you're very familiar with this way back from your high school days, so I won't say much more about it. You all know that penetrating radiation, high energy radiation, is called ionizing radiation, and it consists of those frequencies of the electromagnetic spectrum with very, very short wavelengths, high penetration. There are many excellent presentations on the electromagnetic spectrum online, YouTube, and so on. I'd encourage you to look at a couple if you're unfamiliar with this, but it's fairly straightforward. One of your main barriers in radiation, as with many other topics, is terminology, and you have to absorb a fair bit of terminology to understand what we're talking about. So we'll start with this slide, absorbed dose. As the name implies, the absorbed dose is a radiation metric used to measure the amount of energy absorbed by a kilogram of substance, in our case by a kilogram of tissue, simple as that, and is measured in gray. The equivalent dose is another metric and is simply the absorbed dose multiplied by a weighting factor that corrects for the different effects due to different types of radiations. Simple. And the effective dose is also multiplied by another weighting factor that determines the susceptibility to harm of different types of tissues. And the latter two, equivalent dose and effective dose, are measured in sieverts, or millisieverts and microsieverts, most likely. There's no option but to learn the terms and remember them so you know what they mean when you read them in a journal or somebody mentions it. This is a slide I've added with a lot more words describing what those 3 terms mean, but if all you remember is that absorbed dose is the energy deposited in 1 kilogram of tissue, equivalent dose is the absorbed dose weighted for the harmful effects of different types of radiation, and the effective dose is the equivalent dose weighted for susceptibility to harm for different tissues. You'll be okay. I've added this just to show you that if you read more words, it doesn't necessarily make it any clearer, but it can add a little more explanation, such as the units of measure and possibly a little bit of extra information. There is one other term here, exposure. Exposure has a specific meaning in radiation physics, although it also can mean simply we are exposed to radiation the way we are exposed to sunlight. But in physics, exposure is specifically a measure of the quantity of ionization per unit mass of air. Simple as that. It's not commonly used anymore, but you will still read papers that have that as a radiation metric, and it's useful to know what it actually means. There are other radiation metrics, in this case specific to the cath lab. Fluoroscopy time I mentioned in my lecture, which was an overview of how we can use all these measures of radiation, specifically in the cath lab, to analyze data and keep track of patient dosages. It's a legal requirement to record certain radiation measures, metrics. Fluoroscopy time is one, dose area product is another, and there are others. If you read my papers, don't dwell on them too long. They're just an indication of how we collect data in the cath lab, how we analyze it, how we interpret it, and how we report it. And it's also useful to understand how this data is presented in a scientific manner. You will be reading lots of similar types of papers during your career. You may as well start now and become familiar with them. So I hope they're of interest to you, but don't dwell on them too much. There's a lot of reading for you to do from now on. Fluoroscopy time. Fluoroscopy time is simply a time stamp. It's the number of minutes that the x-rays were on, foot on pedal time. Simple as that. We record it for each case. Dose area product is more specific. It's called DAP, and it's a measure of the entire amount of energy delivered to the patient. And it's defined mathematically as the absorbed dose times the irradiated skin area. A simple calculation that is done automatically by the X-ray machine. And that is still the most convenient measure for assessing patient dose, widely used and a mandatory recorded metric. The absorbed dose, again, is the energy deposited in a small volume of tissue, 1 kilogram specifically. Staff dose is directly proportional to the patient dose, which is DAP, which depends on the actual dose generated by the X-ray machine. So that quantifying DAP provides a standardized basis from which to determine potential staff risk or patient risk per procedure. For example, a pregnant nurse needs to be aware of a record of her radiation exposure to radiation during her work. There is one other term I haven't mentioned in the lectures that I will mention here. It's called air kerma. Now, air kerma stands for kinetic energy release per unit mass. And air kerma is really a theoretical measure of radiation, and it's a measure of the radiation delivered at a reference point, which is taken to be a point 10 centimeters below this patient's skin at the entry point. And that value multiplied by the irradiated skin area gives you what's called the air kerma product, which sounds like dose area product. And they're in fact almost identical measures. They vary by a tiny little fraction that is mostly ignored. But as I said, it's a theoretical value that has its uses. And air kerma is another mandatory requirement to measure. I mention it now because you will read about it in your radiation reading, and if you attend conferences that talk about it. We'll move on. There are other terms to remember: stochastic versus deterministic. Nothing difficult about it. Stochastic simply means random. And these are my words that follow. Exposure to radiation can result in harmful effects. The risk of cancer increases with radiation dose but has no minimum threshold. The long-term stochastic effect of radiation is therefore the probability of developing cancer or a heritable genetic disorder as a direct result of radiation exposure. Nevertheless, there is no evidence that radiation induces hereditary defects in humans, not even in survivors of Japanese atomic bombs. That may surprise you that there were no more two-headed babies born to survivors of the Nagasaki and Hiroshima explosions than there were in non-irradiated populations. It's never been proven in humans that this can happen. The main concern is the development of cancer, although animal studies have indicated that it is possible in animals to induce hereditary defects following exposures to large amounts of radiation. So stochastic is simply the potential to develop cancer following radiation exposure. Deterministic effects are immediate, on the other hand, and they're a direct result of injury from radiation. The severity of injury varies with dose and has a minimum threshold. And an example of this is skin redness after a cardiac catheter, and the threshold for this is 3 to 5 gray, to give you an idea of the amounts of radiation involved. Deterministic effects and stochastic effects are the biological effects of radiation. Deterministic effects are listed here. There can be cataracts, skin burns, vomiting, individual cell death. It has a minimum threshold, and the severity is related to the dose. and the effects occur fairly shortly, even hours after exposure. Remember, it has a threshold. Stochastic effects, on the other hand, are long-term, such as the development of cancer. That's the main concern. It results from DNA damage to a single cell. And there is no minimum threshold. Two people exposed to the same minimum amount of radiation may have totally different stochastic effects down the track. One may develop cancer, the other one may not. And the severity is independent of the dose. The effects occur after years, and there is no minimum threshold. In terms of radiation protection, time, distance, and shielding are your friends. It's obvious. The further away you are from the radiation source, the less time you spend near the radiation, and the more shielding you use, lead gowns, the less likely you are to be receiving radiation. The inverse square rule applies to distance. Stepping 1 meter back from the source of radiation reduces your radiation absorption by fourfold, and so on. Shielding, we've mentioned that, important. And one other important piece of information to know is that radiation is not a constant variable around the X-ray tube, the source of the X-rays. It varies because most of the radiation you receive is patient scatter. This is looking at the patient from the head. The radiation beam is tightly collimated, meaning tightly contained until it hits the patient or the table, and then scatter comes off in every direction. And the scatter patterns can be mapped. And we find the intensity of this radiation scatter varies with position around the patient and is highest in the left side of the patient, the left anterior oblique positions. You must be aware of that. It helps to avoid those hot areas in the lab. That's enough for radiation. Each of these 3 topics will be covered reasonably briefly. It's my intention, because I can't cover what you've already read because you haven't read it, to serve as an introduction to the more difficult topics that you're going to cover in your lectures. So that's what I'll do. I've picked what I think is the harder slides and explained them, which might make it easier for you when you come to reading it. And this is an example. We're going to talk about transducers and pressure measurement. And there's another set of new terminology to learn, and that may be the hardest part of this topic. We're going to talk about frequency response curves. We'll start by defining sensitivity. Intuitively, you all know what it means. Specifically here, we refer to the ability of a sensor to detect small changes in pressure, and is defined as the ratio of the output amplitude over the input amplitude. Now, you've learned about waves, wave mechanics before in high school or in first year, and you know about frequency and amplitude. Let's think of the aortic pressure wave, systole over diastole 120 over 80. Let's assume it's perfectly symmetrical, like a sine wave, and that the mean value, say, is 100, so you have a deflection of plus or minus 20 above that 100 baseline. So the amplitude is 20 millimeters on either side. Now, if we want to record pressure correctly, a pressure wave coming in of 120 over 80, our sensor has to be able to record the output amplitude as equivalent to 120 over 80, meaning if the input amplitude is 20 millimeters above the baseline, the output amplitude has to be 20 millimeters. It's no use to us if an input pressure of 120 systole is reported as 121 or 130, any more than if the diastolic pressure, which is 80, is reported as 79 or 81 or 85. The ratio of the output amplitude over the input amplitude has to be 1. And more specifically, at a heart rate of 100, the sensor might be correct, but what if the heart rate goes up to 120? The frequency increases. We want the output amplitude over the input amplitude ratio to be constant, meaning 1, over a whole range of heart rates, over a whole range of frequencies, whether the heart rate is 20 or the heart rate is 200. And that is defined as the frequency response of a pressure measuring system. It's the ratio of the output amplitude to the input amplitude over a range of input frequencies, so that 120 over 80 measurement has to be constant, irrespective of the frequency of the heart rate, whether the frequency of the heart rate is beating at 20 beats per minute, 100 beats per minute, or 200 beats per minute. Now, sensing membranes has what's called a natural frequency. Think of a gong. If you shock inside it by striking it with an object like a hammer, it will vibrate at a certain frequency. And the frequency will depend on the size of the gong, the thickness of the gong, the material it's made from, whether it's plastic, wood, or metal, the size of the hammer, the density of the hammer, the diameter of the gong. Many factors come into play. The point is, every sensor system, every measurement system, every sensor has its own natural frequency. Say that sensor with a natural frequency of 100 hertz, 100 cycles per second. If a signal, an incoming input signal, has the same frequency or even a frequency close to that, say a heart rate of 95 to 105, even slightly different, that input signal will be recorded as an amplified value, so that the amplitude of the input signal is magnified greatly as the frequency of the input signal approaches the natural frequency of the sensing membrane, that is its own oscillation rate. That is called resonance, and it's an annoying feature of sensing systems. An example of this is a bridge collapse years ago in America. A steel and concrete bridge started buckling like sine waves because the frequency of a strong wind just happened to coincide with the frequency, the natural frequency of that bridge, and it destroyed the bridge. That's just an example of amplification of an output signal as the frequency of the input signal approaches the frequency, the natural frequency of the sensing membrane. So how do we manage this? We manage this by introducing damping. And optimal damping is a means of achieving a balance between sensitivity, damping, and frequency response. Now, if all these words don't have enough meaning to you, they'll be explained in the next slide more clearly, and they're covered nicely in the lecture as well. But hopefully, this will have it explained before you read it. Now, we evaluate the frequency response of a pressure measuring system, any sensing system, by means of a frequency response curve by using what's called a Bode plot. Hopefully, it will all become clearer in the next slide. Don't be scared of this. It's just a graph with a few lines, and all we need to do is look at one line at a time. On the vertical axis, we have the amplitude ratio, what I mentioned. The ratio of the output signal over the input signal. And on the bottom, we have the input frequency as a percent of the natural frequency. So that if the natural frequency of 100 is 100 hertz, and your incoming signal has 100 hertz, that's the point of equality, expressed as a percentage. 100% means one signal is the same value as the other. And this is the point of equality, so that if your natural frequency is 100 hertz, say, and your incoming signal is only 20 hertz, it's no problem. The output to input ratio is correct. But as the frequency of the incoming signal approaches the natural frequency of the sensing membrane, the output signal goes gaga. It's just amplified out of range. So that these curves, the top one represents a totally undamped or virgin signal that we have made no attempt to correct. If your heart rate is coming in at a frequency of 100 beats per minute and your pressure is 120, the sensing membrane, uncorrected, will record a pressure of 200 or more. What we can do is introduce damping, and we can measure this by means of a damping coefficient. An undamped system has a damping coefficient of 0, maximum damping is 1. So if you introduce some amount of damping, that augmentation, that exaggeration of the output signal is suppressed. If you introduce even more damping, then it's suppressed even more. But that signal is still called underdamped, in that it needs more damping to be a true value, to be exactly, say, the 120 milliliters pressure. Ideally, you want an amplitude ratio, a ratio of output signal to input signal, to be 1.0 for the entire range of measurements that you're likely to take. That is simply not possible, hence this discussion. So what we can do is we can introduce optimal damping. And damping is simply, in its simplest form, is friction. And there are different ways of achieving it that we don't need to know about. But consider your heart rate of, say, 100 beats per minute. That's your frequency. And consider your pressure 120. If the natural frequency is 100, then you can't measure a value of 100 unless you have proper damping. And it can be achieved electronically, but only up to a point. So how do we cope with this? Well, apart from introducing damping, we simply choose a sensor with a natural frequency that is huge, say 1,000. If the natural frequency is 1,000 and your reproducible range is only around, say, up to 40% as a straight line, your amplitude ratio, then if your heart rate is 100, your reporting signal will be around here. So we choose a sensing system with as high a natural frequency as possible, and we introduce optimal damping, and that eliminates the problem. It's worth reading the legends here. This is my words again. Damping effects can be analyzed with a Bode plot, a graph that demonstrates how a recorded signal, that is the output signal, is amplified as the input pressure wave, that is the input signal, approaches the sensor's natural frequency. Sorry, that's a little typo. Each line is the sensor's response to an input frequency. And it's also worth reading the proper legend, frequency response curves of a pressure measurement system, illustrating the importance of optimal damping. The amplitude of an input signal tends to be augmented as the frequency of that signal approaches the natural frequency of the sensing membrane. Optimal damping dissipates the energy of the oscillating sensing membrane gradually and thereby maintains a nearly flat frequency response curve, a constant output-input ratio signal, as it approaches the region of the pressure measurement system's natural frequency. Now, I hope that helps you understand the lectures when you come to it. If not, I'm sure the lectures will clear it up for you anyway. It's a difficult concept, particularly the first time you strike it. But all we can do is move on. The only other difficulty, and it's not that difficult, I think it's quite simple. I think a 5-year-old child can reproduce this. It's the strain gauge. Let's have a look at the strain gauge. The strain gauge is simply a representation of the design of a transducer, and a transducer is what we use to measure blood pressure. It's about the size of a thumb drive, and it's connected to the patient via a little pressure line, simply plastic tubing, to the inside of the patient's artery, so that when you have a heartbeat, systole will deflect this little membrane. So it's a box containing a little box inside, and the box is split into two by a flexible membrane. The left side is fluid-filled, saline and blood at the end of the line to receive the fluctuations in pressure due to a patient's heartbeat. The right side of the box is air-filled, and it's open to air by this little port. And inside is a little electric circuit, such that it consists of 4 resistors attached to this little plunger. When a heart beats in systole, that membrane deflects and moves the plunger to the right. That lengthens this little wire and shortens that one. And you know from Ohm's law that as you stretch a wire, you decrease the diameter and therefore increase the resistance, having the opposite effect on the shortened wires. With diastole, that plunger returns and has a reciprocating effect. This is called a strain gauge. You should be able to draw this in your mind. I'm sure a 5-year-old could do it. Think of it as a little box within a box, separated by a membrane, open to the patient on one side, open to air on the other, with your little electrical circuit. It's worth reading the legend. Schematic representation of a strain gauge transducer. Pressure is transmitted through port P and acts on diaphragm D, which is vented to atmospheric pressure on its opposite side. Pressure causes the diaphragm to stretch, in turn stretching and therefore increasing the resistance of wires G1 and G2, having the opposite effects on G3 and G4. Simple concept, very clever. We'll see how this is applied in this slide. This is called a Wheatstone bridge circuit, and it's simply an application of the strain gauge we saw before. Again, it's a simple circuit. It's just a box connected to another little box on its edge. And the big box has a battery connected to it. And we can put a little sensor, a voltage sensor at this point, and another voltage sensor at this point to measure the voltage difference. And these are the 4 resistors we had before. Now, as the plunger moves with systole in that strain gauge, the resistance in G1 increases, while the resistance in G3, its partner on the right, decreases, meaning that exactly half the voltage of battery B occurs at this point and that point, because the current splits into exactly 2 halves. When your heart beats and G1 is stretched, the resistance here increases and the resistance there increases, and the resistance here decreases, causing an imbalance in the circuit, and through the magic of electronics, current flows. And the change in current is directly proportional to the change in pressure that elicited that deflection in that membrane that caused the change in resistance. It's worth reading this. Strain gauge connection of the Wheatstone bridge. In this arrangement, if all resistances are equal, then exactly half the voltage of battery B exists at the junction of G1 and G4, and half at the junction of G3 and G2. Therefore, no current will flow across these 2 output terminals. However, when pressure is applied to the diaphragm in the previous slide, the resistances are unbalanced, so that the junction of G1 and G4 becomes negative because of the greater resistance, less currents flow, and this point becomes negative relative to that point, and a current flows across these 2 output terminals. You should be able to reproduce that in your mind, and you may be asking yourselves, why are we learning this? Well, we are the operators. You operate the transducers that give you your echo images, and you need to understand the nature of ultrasonics. We are also more than just the operators. We're not just the bus drivers. We're also the mechanics and the engineers, and we need to be able to fix things when they go wrong. And understanding how things work is a big step forward in doing that. That's why they call us techs. We must be able to troubleshoot when things go wrong, as I've just said. If there is no pressure trace, the problem is either the transducer itself, the connections to the transducer, a cable somewhere, or a failure of the entire system. And this is part of your troubleshooting chart that you will be taught. Always check the connections. You know, a loose or wet connection simply doesn't work. Check the cables. Amazing how many trolleys run over cables and break them. Check the transducer is flushed and zeroed correctly. You will be taught all this in your prac classes. Check the monitor settings. You may be on the wrong channel and that the scales are correct. The transducer may zero and not detect pressure, or the transducer may fail to zero. There are steps you can take to determine which. And you have to decide whether to replace the transducer, reboot the system, or some other approach, and always keep the faulty transducer for testing, just to confirm your diagnosis. That's enough on that topic. Let's move on to pressure waves. Your first entry into hemodynamics. A lot of this might be new to you, but it can be simplified, and that's my job. Simplify things so that you can understand them. You will come across only 3 basic blood pressure waveform types. They're shown here. You're familiar with your aortic pressure trace or any arterial pressure trace, systole, diastole, and mean. I used this illustration as a sine wave for the transducers, and I took the mean to be the baseline value, and the deflection from the mean I took as the amplitude. That's not strictly correct because it's not a perfect sine wave. Never mind, this is what an arterial line or an arterial pressure trace looks like. Systole, diastole, with a mean repeating over and over. You learn this trace, memorize it, recognize it, you just know it. That occurs in all arteries. Another type is the ventricular trace. It's systole and diastole, no mean, but whereas the aorta is a muscular tube with residual tension, The ventricle, after it contracts, becomes a big floppy sac. So despite its strong contraction generating a high systolic pressure, when it relaxes, it whittles down to zero, near zero. And then it fills with blood and it contracts again and pressure shoots up. Appreciate the difference between these two. Notice the scale. This is 200 and 100, so 0 is down here. So the arterial trace operates along the upper part of the curve of the ventricle, whereas the ventricle drops down to near 0. The baseline is 0. Top value is around 200. Can be greater, of course, but most of our charts measure on scales of 0 to 200 to record arterial pressures. These two aren't difficult. They're monophasic, meaning there is one cycle per heartbeat in both. The only difference is in the aorta, the next heartbeat kicks in before the pressure has dropped below a certain value. Whereas in the ventricle, it drops down to the lowest it can and it starts filling with blood again and pressure builds up and then it contracts. Simple. You should remember these two forever now. The third waveform type is what I referred to as a biphasic venous type. That's a loose description of my own. Biphasic venous. Notice for every heartbeat, these are all in sinus rhythm. This biphasic waveform has two little deflections. They're called A and V waves. And we also measure the mean. And they will look something like this in every case, except there will be variations due to pathology. But if you remember these three basic waveforms, you will have no problems. This comes from the right atrium, and it's the same in the left atrium and any vein. Central veins, of course, in particular, is the one we're interested in. And it will also occur in a couple of other little circumstances that we won't go into now. Just remember the differences. Monophasic, high pressure values, scale of 0 to 200. These are low pressure systems because they occur in the right ventricular side of the heart. These are the left ventricular side. Systemic, and these are associated with the right atrium. Three basic waveform types. Can't get much simpler than that. Remember these and you'll be okay. Let's have a look at what pressure waves look like in our traces. This is a catheter inside our right coronary artery doing an injection. There's the right coronary sinus. It's in the LAO. You can see the backbone is on the right and the ribs are sloping to the left. And the catheter has engaged the right coronary artery, and the right coronary didn't like that, and it suddenly went into spasm. It gripped the artery at the ostium and started constricting. That happens occasionally, particularly with normal arteries that don't like being irritated or being injected with dye, deprived of oxygen. They're not used to it. This is what happens in your trace. Suddenly, when that spasm occurs, pressure will drop. And that's an expression of damping. Anything that interferes with the transmission of the natural energy of a pressure waveform is called damping. It obliterates that pressure trace. We don't know the cause of that necessarily unless you were watching that. And immediately that happens, you have to call out damping or some such thing to attract the cardiologist's attention, who will be cluey enough to know that as soon as he engaged that happened and this caused the pressure trace. Usually they can tease it out and restore normal flow. This was resolved by giving the patient a vasodilator, GTN, which restored the normal diameter to that vessel. This is before the GTN injection, showing that sustained constriction of that ostial area of the vessel. This is just to show you what we find in the cath lab in live cases. This is another example of it. This patient had a clot in the catheter. The cardiologist and the nurse are supposed to keep on flushing the system regularly. Sometimes we give heparin, sometimes not. In this case, this trace appeared. I immediately reported it at the time and action was taken. The catheter was withdrawn. It was flushed to remove any residual clot. It was probably exchanged with a new one. Heparin might have been given and reinserted. And once the clot was removed, this is the pressure we received. I can't recall other details of this case, but you see the pressure is low and steps would have been taken to increase that pressure. And you notice the rhythm. It's some kind of idioventricular rhythm. We won't go into it. It's not a 12-lead ECG. But again, we have to be attentive to these sort of artifacts that occur and recognize them. So you will go through all this, but remember, Your role will be to always zero correctly, set up the transducer appropriately, zero repeatedly as you see fit. The cardiologist and the nurses who are scrubbed and sterile will flush the system frequently. Remind them if they don't. Record pressure at mid-chest level every time you record or zero. Be paranoid about air bubbles. If you see any damping effects, always call it out. It could be an air bubble about to be injected. And monitor for other damping effects like the two you've just seen. Leaks in the system. If a pressure drops, it could be a leak, could be a catheter kink, could be thrombus formation. And remember that because it's sterile, contamination is a serious issue, so you're not part of that. You're not scrubbed. You're attending to the instruments. This is a summary of where you'll see those three waveform types, the 6 cardiac chambers, the aorta and the pulmonary arteries, structurally and physiologically very similar. Therefore, they have similar pressure traces, that monophasic arterial trace. The ventricles, structurally and physiologically very similar, both floppy sacs when they stop contracting and relax. High systole, low diastole. The only difference is in the scale of pressure generated. Systole here 20, systole here 120. And the other two, the atria, these are the biphasic waveforms that are referred to. And you can see here A and V waves. There can be another little blip called the C wave. And one of the other sites is in the pulmonary circuit. We'll look at that in a later lecture. All this comes together, of course, in your Wiggers diagram. And however complicated this may appear, and it was frightening the first time you saw it, and I believe some of you struggled with it, there are only three waveforms. The arterial waveform here, the ventricular waveform here, and that biphasic waveform here. The trouble is it's stretched out and it's an exaggerated distortion of the real trace. It's synchronized with the ECG, and this is separating the left side with the right side. When I draw a Wiggers diagram, I just draw this 0 to 200, and I put another little scale here, 0 to 40, and bang. If you use this scale, you've got your right side of the heart. If you use the 200 scale, you've got the left side of the heart. So you can eliminate this if you wish to. And remember, it's easy to separate systole with diastole, atrial systole, ventricular systole, and so on. Depends on your terms. You have to be specific when you're talking about the two together. And it's easy to recall that your P wave precedes your atrial contraction, and your QRS immediately precedes your ventricular contraction. And you have your periods of isovolumetric contraction and relaxation. You've got your dicrotic notch, and you have your volume changes. And this also be useful in interpreting your sounds, but your guide is your points of valve opening and closure. Review this, it is important, particularly in understanding hemodynamics, that we will see more of. The intent is to integrate the tutorials with the lectures in a way that each complements the other. This is a little difficult if, as we are aware, we haven't read the lectures yet, but if this helps to introduce these new concepts and all these new terminologies into your reading and your understanding, then we're making progress. With that, I'll end this tutorial.